Hi guys, this is Marco with Students Teach Orgo. Today we're going to talk a little bit about primary amine synthesis. So we're just going to go right ahead into some of the methods that we use to make primary amines. The first main one is using some chemistry that you should already know with cyanide. So we react this alkyl bromide here with the cyanide salt, and the cyanide will replace the bromine, so we'll get this alkyl cyanide, and then we can go ahead and reduce the nitrile bond here, the triple bond between the nitrogen and the carbon, using something like lithium aluminum hydride, and then treat it with some water afterward, and then that will convert the cyanide into this amine here. Now you'll notice that this product here has one extra carbon compared to the initial reactant, so just keep that in mind when you're doing a reaction with cyanide. If you're trying to get a product with an extra carbon in the chain, then use cyanide. We can use a similar reaction with this methyl cyanide, I guess you could call it, if we want an extra 2 carbons in the chain, right? So we take this methyl cyanide, treat it with LDA and this isobutyl bromide, which is just this. I just wrote it out as an abbreviation instead of drawing it out. But if we treat it with this methyl cyanide instead, then we will add an extra carbon onto the chain where the bromine initially was, and then we have the cyanide group adjacent, and then again we can treat with lithium aluminum hydride and water, and then that will give us 2 extra carbons in our chain, and convert the nitrogen to an amine nitrogen instead of a nitrile nitrogen. Another common method is using azides, so very similar to the last mechanism. Instead of treating with a cyanide salt, we treat with an azide salt that will replace the bromine on the alkyl bromide with the azide group, and then we can do one of 2 things. Either we can use lithium aluminum hydride and treat with water again to reduce the azide and create our amine, or alternatively we can use this triphenyl phosphine group and treat it with water, and then that will have the same kind of effect. This second option here is called the Staudinger reaction. You don't really need to know that, but it's nice to know in case you ever come across it doing a problem. So this triphenyl phosphine and water, that is the Staudinger reaction, and you can do either the reduction up here or the Staudinger reaction. That gives you the same thing. Another common method is the Gabriel synthesis. This uses a particular reagent called potassium phthalimide. So that's this potassium salt right here. The potassium ion doesn't really take part in the reaction per se. So we take our alkyl bromide again, we react it with the phthalimide group, and that will kind of attach onto the nitrogen. The nitrogen here will displace the bromine, and the alkyl group will attach to the nitrogen there. After that step, we can then treat with, well, we have 2 methods for treatment, again, just like the last thing. We can use hydrobromic acid and acetic acid, and then that will kind of cleave the phthalimide group off, and then leave you with this this protonated amine compound here. Or alternatively, you can hydrolyze this up here using hydrazine, so this molecule H2 and 2H2, and that will create a separate byproduct. So here, where we have these 2 carboxylic acid groups in the byproduct, we now end up with these 2 amide groups in the byproduct. So you can use either thing. It will give you the same kind of amine, just a different byproduct. And then finally, to convert this protonated, or to deprotonate this amine, we could just react with a strong base like NaOH, and then that will do the trick. So then we end up with the amine. And so for this reaction, we just basically convert the Br to an amine group. A little bit more complicated now is the Curtius rearrangement. Now this one has some funky chemistry. We start with an acyl chloride up here, and then we treat with an azide salt, just like the azide reaction that we looked at before. The N3 minus group will replace the Cl So the Cl minus will become a leaving group, and then we end up with this azide compound here. And this these two outer nitrogens on the azide make for a very good leaving group, right? They leave as nitrogen gas. So by heating the reaction up a little bit, this occurs, and that leaves us with this very interesting nitrene intermediate where this nitrogen here has two lone pairs but no formal charge. So that's kind of an interesting and quite rare thing for organic chemistry. So what ends up happening here is one of the lone pairs becomes a double bond with this ketone or amide carbon right here, and then this bond on the other side of the carbon kind of moves over and becomes bound to the nitrogen instead of the carbon. So after applying some heat to facilitate this, what we end up with is this isocyanate intermediate. And then this isocyanate intermediate we can react with water, and that will create our amine. And then this O and C here will pick up another O from the water and leave as carbon dioxide. So yeah, my recommendation would be to spend some time with trying to grapple with what exactly is happening in the nitrene step, because that's not very common. And so to kind of summarize the products of this reaction, we start with this acyl chloride, and this R group here on the left hand side of the acyl chloride kind of stays the same, and we're just replacing this acyl chloride carbon with our amine group. Okay, and very similar to the Curtius rearrangement, but a little bit different is the Hoffman rearrangement. Here we're starting with an amide as opposed to an acyl chloride, and we treat, instead of using azide, we treat with NaOH and Br2. Now this will cause the nitrogen to be bound to one of the Brs and to lose both of the H's, and so the nitrogen gets this negative charge. Because the electronegative bromine is adjacent to that negative charge, it will pick it up and become a good leaving group, so you will have Br minus leaving this compound, and then that leaves us with our nitrene intermediate again, right? And then so from this point, it's basically the same steps as the Curtius rearrangement. One of the lone pairs on this nitrogen will form a double bond with this carbon right here, and then this bond will cleave and move over to this nitrogen. And that will give us our isocyanate intermediate right here. I'm not sure why this stuff is here. I probably forgot to delete that, so just ignore this. But this isocyanate intermediate, and then treating that with water will give you the amine. Quick note about the isocyanate ion. We are treating it with water in our steps in order to produce the amine, but you can also treat it with other sorts of compounds. And then that will give you different products. If you do it with this alcohol, an alcohol like this, you will end up with a carbamate molecule, which we don't really talk a lot about in this course, but it's nice to know. And then if you treat it with a different primary amine, you end up with this urea derivative, where it's kind of like a double amide. You have nitrogens bound to a ketone on both sides, so that's a bit interesting. Okay, now we'll get into some practice problems, so go ahead, pause the video, and come back when you think you have an answer. Okay, so to determine the reactant in this reaction, we first have to see what kind of reaction we're doing. You can see in our steps that this is with some sort of cyanide mechanism and then a reduction. So we can already know, since we're doing cyanide, that we have to take one extra carbon off that chain, right? We're going to take off the carbon adjacent the amine. So here we have our amine, this is the carbon adjacent, so we know that the initial reactant was kind of, if we cleave at this bond, the initial reactant will be the stuff to the left-hand side, right? And then we kind of just add a bromine onto wherever that bond is supposed to be. Right, and so that's exactly what the answer is. We take that extra carbon in the chain, and we say that that is where the bromine initially was, and then that gives us our reactant. And just to show the forward mechanism, all right, we take the bromine, we replace it with the cyanide group, the nitrile group, and then that's the C in the nitrile group, after we reduce it, becomes part of the chain now. All right, problem 2. Okay, so for this, this is a Gabriel synthesis, right? The overall product of the Gabriel synthesis will just have the Br replaced with an amine group. So by keeping this benzene ring and then adding an extra carbon and then an NH2 amine group, that is our product. To go into a bit of the mechanism for this, we have our two reactants to begin with. The bromine will come off, and this part of the first reactant will attach to the nitrogen here, so that's what we get in that first step. And then in the second step, we can cleave it. In this case, we cleave it with HBr and acetic acid, but again, you could do it with hydrazine as well, but that would give you a separate byproduct. So that kind of cleaves these two bonds right here, and leaves us with the NH3 plus group, where our bromine initially was. And then finally, we can treat with base, NaOH, and take off one of the hydrogens that is giving this N a formal charge. And so that gives us our answer, our final amine. All right, problem 3. All right, so for a courteous rearrangement, it might be useful to think of the mechanism for this, which I'll get into in just a moment, but recall that for the courteous rearrangement, the kind of overall effect is that the acyl chloride carbon, so the carbon that's doubly bound to the oxygen, is replaced with the amine group, right? So that this is our acyl chloride carbon that's doubly bound to the oxygen, so our NH2 would go in this spot, and that's exactly what we get. So now going into the mechanism, first we have replacement of Cl by the azide, then the N2 leaving group comes off of the azide, and that leaves us with our nitrene intermediate. There's that, shuffling around where one of the lone pairs on the nitrogen becomes a double bond to the carbon, and this bond on the other side of the carbon moves over to the nitrogen, and that gives us our isocyanate intermediate. And then finally we treat with water, and then that gives us our final product, the amine, by kicking off CO2 as a leaving group. Okay, and then problem 4, use the Hofmann rearrangement for this one. Okay, and then problem 4. Okay, so for the Hofmann rearrangement, we need to begin with an amide for the Hofmann rearrangement. So first we have to convert this precursor to an amide, and then we can react it with NaOH and Br2, and then do the rest of the Hofmann rearrangement. So mechanistically, kind of working backwards, we have this, well, here's our product, right? Okay, so for the Hofmann rearrangement, you kind of want to think going backwards on this one. So remember that the Hofmann rearrangement, the second half of it is very much like the courteous rearrangement, where we have the isocyanate ion and everything. So the overall effect, that the what is initially for the Hofmann rearrangement, the amide carbon, is replaced by the NH2 amine group. So again, kind of working backwards here, this is our product that we begin with. Here is our NH2. So we know that at this position is where the amide carbon was initially. So kind of reversing the step, which is treating with NaOH and Br2, we end up with this amide, right? Again, we're adding this carbon where the NH2 initially was, and then that is kind of the center of our amide, and then we add the doubly bound oxygen and amine groups to make the rest of that amide. And then to get from our, what they give us as our precursor molecule, right, which is this right here, to the amide, we know that with if we have a carboxylic acid, we can just treat it with ammonia and heat, and then that will replace the OH of the carboxylic acid group with the NH2 and create the amide that way. So this is another way to create an amine.